All right, so these are the problems for the energy examples worksheet. Number one, it says a projectile with a mass of 4.3 kilograms is thrown down with a velocity of 5.0 meters per second at an angle of 30 degrees down from the horizontal from a cliff that's 55 meters high. On the way down, the projectile experiences 380 joules of dissipated energy. What's the velocity of the projectile the instant before it hits the ground? All right, so we're going to use conservation of energy, which means the total change in energy is going to be equal to zero. Now, the different types of energies we're going to be talking about, first of all, with velocity, we're talking about kinetic energy. We have a height, so the height here, that deals with gravitational potential energy. And then we have some dissipated energy here as well. Okay, so to set up our equation, basically what we're going to do is we're going to set the energy before equal to the energy after. So we got kinetic energy initially plus the gravitational potential energy initially plus any dissipated energy. Actually, dissipated energy is going to go on the other side. It's going to be equal to the final kinetic energy plus the final gravitational potential energy plus any dissipated energy that basically leaves the system. All right. Okay, so the kinetic energy, the initial kinetic energy, it starts from zero, right? No, it starts with 5 meters per second. So we have an initial velocity. So mass times the initial velocity squared over 2 plus the gravitational potential energy starts with a height, mass times gravity times height. That's going to be equal to the final kinetic energy, which we don't know. And that's kind of what we're looking for too, for the final velocity. Plus the mass times gravity times the final height. So that's the initial height, that's the final height. Final height's going to be 0 at the bottom, plus any dissipated energy along the way. All right, so keep something in mind. Because we're talking about an object that's moving at a 30-degree down angle, that 30-degree down angle actually is not very important because direction does not matter with the energy. The amount of energy it has is independent of the direction. Okay, so you'll see in all of this, we got mass times initial velocity squared over 2 plus mass times gravity times the initial height. That's going to be equal to mass times final velocity squared over 2. The final gravitational potential energy is going to be 0 because it's going to be at the bottom, and then we have dissipated energy. All right, so we start plugging in what we know. So we get a final velocity of 30.4 meters per second. Next problem says two masses on an Atwood machine with a 1.8 kilogram mass being 2.4 meters higher than the 0.3 kilogram mass. If the masses are initially moving at 3 meters per second, what's the final velocity of the masses when they get to the same height? Use conservation of energy. Okay, so we got two masses. And they are a distance of 2.4 meters from each other. So when they get to each other, that means they're going to have a change in height of 1.2 meters. All right, so really 1.2 meters is going to be our change in height for this. All right, so we got the two objects are going to be, if we do conservation of energy, we're going to have kinetic energy of this object over here. That's mass 1, mass 2. We got kinetic energy of this object initially, and both of them are going to be picking up speed. So as far as kinetic energy is concerned, we can really treat both of these as one object because both of them are going to have the same initial velocity, both of them are going to have the same final velocity. So mass 1 plus mass 2 times initial velocity squared. All right. Then we talk about gravitational potential energy. All right, so one starts with, essentially, we're going to say that this is our height of 0. So height of 0 here, and then the other object starts at 2.4 meters above. So mass 1 times gravity times its initial height, which is going to be 2.4 meters up. All right, So that's going to be all the energy there. We're assuming that there's no dissipated energy. So then we take the mass 1 plus mass 2 and their final velocity squared, and that's what we're trying to figure out. We're figuring out that final velocity. And then we go ahead and figure out, let's see, both of these together are going to have the same height. So we got mass 1 times gravity times the final height plus mass 2 times gravity times the final height. Both of them are going to have the same height. It's going to be 1.2 meters above. Okay, so this is our conservation of energy equation. All right, so let's go ahead and start plugging in numbers. Next question, number 3. It says a skier on an icy slope skis down a 13-degree incline on 220 meters before reaching ground level. If the coefficient of kinetic friction of the entire trip is 0.05, how far will the skier go on the level ground from the base of the slope before stopping? And use conservation of energy. Okay, so we're going to have dissipated energy effectively. So we start with some gravitational potential energy, and we don't start with any velocity. So it says she starts at the 220 meters, and then what she's going to do is she's going to slide down, and as she slides down, we're going to lose gravitational potential energy, so all that's going to be gone, but we're going to gain kinetic energy in the process. In addition to this, we're also going to lose dissipated energy. Now the question says, how far will she go before stopping? So she's going to stop again at the end. So what's interesting about this problem is even though we have a speeding up and a slowing down, there's essentially the initial kinetic energy is going to be 0 and the final kinetic energy is going to be 0. So we don't need to include anything except for the change in gravitational potential energies, all going to be dissipated by friction when we get to the very end. Now what I'm going to do is I'm actually going to say I'm going to split this up into 2 parts: dissipated energy 1 and then dissipated energy 2. I know it's terrible notation to have 4 letters as one variable, but we're going to say this is dissipated energy 1, dissipated energy 2. And the reason I've got 2 of these is because this is going to be on the incline as it's coming down, and then the second part is going to be on the horizontal. So number 1 and number 2. The reason both of these matter, the reason there's a difference here is because the normal force is going to be different for this part as it is for this part. And because the normal force is different, then that means the force of friction itself is going to be different as well. So the amount of dissipated energy, meaning the force times displacement, is going to have a different force here as it is for there. All right, so let's figure out the force. The net force, as you're on an incline, is going to be equal to mass times acceleration. So the force of friction, and really, you know what, I don't even need this. What I really need is I need the force of friction is equal to the coefficient of kinetic friction times normal force. And the normal force on an incline is going to be equal to, if you remember, it's going to be equal to the cosine component of gravity. All right, so the force of friction on the first part is going to be equal to the mass times gravity times coefficient of kinetic friction times cosine of the angle. Okay, so the second part, so that's for the first part. The force of friction for the second part It's just going to be equal to the coefficient of friction times mass times gravity, because it's on a horizontal surface, so the normal force is going to be equal to the force of gravity. So there's my two forces of friction. That's why I have two dissipated energies. All right, so we got mass times gravity times our initial height. That's going to be equal to the force of friction 1 times the distance, which is given to us. It says it goes down 13-degree incline at 220 meters, and then it reaches the level ground. So we got force of friction 2, and then I'm just going to go ahead and call this D, and D is what we're going to be looking for, the distance that it travels on that horizontal surface. All right, so go ahead and plug in what we know. Mass times gravity, the height. Okay, so the height here, that height is going to be that side, the sine, all right, the sine of this triangle. So that total distance, which is the displacement, so displacement, let's see, h, go ahead and do it over here. H is going to be equal to, let's see, the sine of the angle is opposite over the hypotenuse. So h is going to be equal to delta x sine of theta. Delta x sine of theta. So delta x sine of theta, that's going to be equal to the force of friction, which is mass times gravity, times mu of k cosine of theta times delta x, plus this portion right here, which is just mu of k mass times gravity. All right, so going through this a little bit, you can see that some of this is actually going to cancel. Mass is in every single term, so that cancels out of each one of these. The acceleration due to gravity, that's in every single term, so that will cancel out of here. Okay, D is what we're looking for. So we go ahead and take this term to the other side and divide by mu of k. So okay, so go ahead and plug this in. We get a distance of 1,649 meters. And of course I'm in radian mode, so that's wrong. Let's try this again. There we go. 775 meters. So that was radian mode. My bad. That looked wrong. Anyway. All right, so the distance, 775 meters. All right, so the next question says, suppose a car is traveling 5 meters per second, requires a force of 27,000 newtons to maintain a speed for 3 seconds. What's the work done by the car engine? Okay, so the work done by the car engine, basically what we have, since we're moving at a constant speed, then that means that the engine's pushing forward with as much force as the air resistance is pushing back. So the work done is going to be equal to force times displacement, and both of those are in the same direction, so it's going to be positive. So the work is going to be equal to, and this is part A, the work is going to be equal to the force, which is 27,000 times displacement. Now displacement is not given, but it does give us the velocity times time. All right, so 27,000 times the velocity, which is 5, times time, which is 3. So 27,000 times 15. That gives us 405,000 joules, or 405 kilojoules. Now, the interesting thing about this is that we have, for part B, that we ask for the work done by air resistance. Well, the force that's pushing forward is the engine, and the tire is pushing it forward, but the air resistance is pushing back on it. So the work is actually going to be equal. So the work for the engine here, the work for the air resistance is going to be equal to the negative work of the engine, because that's going to give you the total power, or I'm sorry, the total work on the system is going to be 0, since we're not accelerating, we're not changing our velocity. So if you remember the work energy theorem, the total work done is going to be equal to changing kinetic energy. So the force that's being applied forward does positive work, and the force that's going backwards, which is the air resistance, that's going to give us negative work. So 405 kilojoules. 405 kilojoules. All right, so the next one, part C, it asks what's the power developed. All right, so the power is going to be equal to work over time. So work over time, so that's 405,000 over 3, and that gives us, divided by 3, gives us 135,000 watts. And that's going to be the same as 135 kilowatts. Now, what you may notice, I'm not sure if you remember this, but the force times velocity, when something's moving at a constant speed, you could take the force times the velocity, which was 27,000 times the velocity, which was 5. And if you multiply those together, you get 135,000 also, which is 135 kilowatts. All right, so either way, you can get the same answer. On the back, number 5. It says that suppose a car is traveling 8 meters per second and requires a force of 27,000 newtons to maintain the speed. What's the power developed? So again, the power is going to be equal to the force times the velocity. All right, and the force times velocity, that's going to give us 27,000 times 8. And in this instance, 27,000 times 8 give us 216,000. That's watts, or 216 kilowatts. All right, number 6 on the back. It says a bungee jumper jumps off of a ledge and bounces back up. Draw an energy diagram for the following points in his jump. Assume that there is no dissipated energy. All right, so about to jump, that means he's going to be at the top of his path. That means at the top of his path, that means he's not moving, and he doesn't have any spring energy because the bungee cord acts as a spring. So he has all gravitational potential energy. All gravitational potential energy. All right, so when the jumper falls, where the cord is about to stretch. So if it's about to stretch, then he still has some gravitational potential energy because he still has a way to fall, to come down, because as it stretches, it's going to fall downward. But he's also going to be moving, so he has some kinetic energy as well. All right, as he fell, the gravitational potential energy converted over to kinetic. And then at the bottom, where it says the cord is fully stretched, when the cord's fully stretched, we have no gravitational potential. And when the cord's fully stretched, he's also stopped. So that means that there's no kinetic energy, and all of it is going to be in spring potential energy. Now, one thing I want you to notice about this is the amount of energy I start with is equal to the amount of energy I end with, because I have no dissipated energy at all. Also, every path along the way, or every part along the way, the total amount of energy doesn't change. I still have 3 levels high. I don't really know how much that energy that is, but it's 3 levels high. So I have 1, 2, 3 here as well, and 3 there. So this shows a couple things. Number one, it shows that the amount of energy every time is the same, regardless of where that energy is. The second thing it shows is that energy transfers from one type to another, from gravitational potential energy over to kinetic, and then at the end, the kinetic and gravitational potential energy converts over to spring potential energy. Number 7, it says that a 3 kilogram mass is attached to a spring horizontally on a frictionless surface. The mass is displaced to the left of the equilibrium position and then released. The mass gets back to the equilibrium position and moves at 10 meters per second. What work is done by the spring? What work is done by the spring? All right, so the work that's done is going to be equal. The work that's done is going to be equal to the amount of spring energy that's put into it. But also, if you think about it, work equals change in kinetic energy. Change in kinetic energy. So if you know the change in kinetic energy, which is 1/2 mass times final velocity squared minus 1/2 mass times the initial velocity squared. The initial velocity is 0, so that part goes away. So 1/2 times the mass, which is 3, times the final velocity, which is 10 squared. Half of 3 is going to be 1.5. 10 squared is 100, so 1.5 times 100 gives me 150 joules of work done. All right, so that's how much work is done by the spring. Part B, if the spring was originally displaced 5 centimeters from an equilibrium position, what's the spring constant? Okay, so this is where we have kinetic energy and spring potential energy. So what's the initial and how does that transfer when we talk about the final? All right, so we have no change in height, so we don't have to worry about gravitational potential energy at all because we're dealing with a horizontal surface. Okay, so kinetic over to kinetic over to spring potential energy. So all of it is in spring potential energy at the beginning. All of it's compressed. So that's 1/2 K times whatever it's compressed squared. So that's the initial compression. There's no initial energy, kinetic energy, because it initially starts at rest. Then at the end, at the equilibrium position, we have all kinetic energy. So mass, 1/2 mass times final velocity squared. But we don't have any spring energy because at the equilibrium position, there is no spring energy left. All right, so what we have here, notice that this right here, that is from here, we can go ahead and just plug in that number. So 1/2 times K times the original compression, which is 5 centimeters, that's 0.05 squared, is going to be equal to 150 joules. All right, so multiply by 2, that gives me 300. And then we divide by 0.05 squared, which is 0. I believe that's 0.0025. And then you divide those two, you get a K value. Let me just confirm that it's 0.05 squared is 0.0025. Okay, take 300 divided by that, and we get 12 with 4 zeros. That's newtons per meter. So it's 120,000 newtons per meter for our K value. All right, last problem, number 8. It says, for a person with a mass of m swinging at the end of a rope of a length L, if the person has originally displaced a small angle theta from the bottom, determine the function of the person's speed v at the bottom of the swing. All right, so we're going to treat that person like a point mass. That object is going to swing downward here to this point at the bottom. Okay. So, person of mass m, I don't know what their mass is, but, well, I know that it's m, but I don't know the actual number, so I'm not going to be able to do anything with my calculator on this. The length of the string is L, and then we have a small angle of theta. Okay, so what's the v? What's the speed at the bottom? Okay, so as it comes down, we're going to convert over from gravitational potential, because we have some height that we start at, down to kinetic. So we have gravitational potential initially, and that's going to be equal to my final kinetic energy. All right, so mass times gravity times the initial height is going to be equal to 1/2 times mass times the final speed squared. Rearranging this equation, the mass actually will cancel, all right? And then the final velocity squared will be equal to, bring this 2 to the other side to get 2g, and then the initial height. Okay, so now g, I know, that's going to be 9.8. But the initial height, what's the initial height? Okay, so it starts with a height up here that's above. When it gets down to the bottom, it's going to be a distance of L from this pivot point. So the question is, what is this part? How far is that? Okay, so if the hypotenuse here is L and this angle is theta, then this side of this triangle right here is going to be L cosine of theta. And the full length is going to be L. So H is going to be that total distance. So to find this distance here, I take the total distance, which is L, subtract off this distance up here, which is L cosine of theta. All right, so I'll plug that in over here. So the final velocity squared is going to be equal to 2g. And what you notice with each of these terms, L minus L cosine of theta, is both of them have an L in common. So we factor that out and we get 1 minus cosine of theta. All right, so then the final velocity, that final velocity is going to be equal to the square root of 2gl, quantity 1 minus cosine of theta.